Hi, my name is Prithviraj Prabhu, and I'm here to talk about fault-tolerant syndrome extraction and catch rate preparation with fewer qubits. Throughout this talk, I'll be focusing on syndrome extraction because the methods and the techniques we use to get our results can directly be used for catch rate preparation. So let's jump right in. Assume you have a group of qubits and you somehow manage to put them into a quantum error correcting code. In order to perform ideal quantum error correction, you will need at least one extra qubit. But unfortunately, we don't live in an ideal world. So in fact, we have to do fault-tolerant error correction. And the issue with fault-tolerant error correction is that you require many extra qubits. How many exactly? Well, the upper bound on this qubit overhead was shown to be linear in a parameter W, where W is the maximum weight of a measured stabilizer of the code. It was initially shown to be equal to W plus 1 by Shor, and after a few improvements, it was brought down to W by 2. But in this work, we show that you can bring this down to logarithmic in W. And in the special case of fast reset, where your qubits can reset really quickly, you just need four qubits. To put this into perspective, consider W as like some high number like 1024. If you do so, the existing protocols say you need 512 extra qubits just to perform fault-tolerant error correction. But we say that you just need 11. That's a big decrease. Okay, so before we see what tricks we use to make these circuits, let's talk about the single most important quantum gate that we use in all of our circuits in this talk, the C0 gate. Because we're focusing on quantum errors, let's look at how quantum errors can propagate through a circuit consisting of just C0 gates. An X error on the control wire of the C0 gate can propagate down to the target wire, but an X error on the target wire can't propagate back up into the control wire. On the contrary, a Z error on the target wire can propagate back up to the control wire, but a Z error on the control wire can't come down to the target wire. We can actually use these rules to our advantage to try and catch errors in a quantum circuit. So consider the circuit that I've shown here. You can think of each of these black wires as qubits in the quantum error correcting code. And the red wire on top is the one extra qubit that you need for ideal error correction. So say that your data qubits have a Z error somewhere in them. This circuit, using this circuit, the Z error will propagate up into the red qubit, and it's measured by this X measurement, and it's caught. So this circuit's useful to catch Z errors at least. But the problem with this circuit is that it only works in an ideal setting. If you allow faults to happen while you perform the gates of this circuit, something bad can happen. For example, if an X fault occurred between these two C0 gates, it'll propagate down into two of the data wires into a weight 2 data error. And that's kind of bad because if you have a weight, say 100 stabilizer measurement circuit, then one fault could cause a weight 50 error, which is extremely terrible. So the caveat is that X errors can be kicked back onto the data. So in reality, one qubit is just not sufficient. So if we use extra qubits, you can perform fault-tolerant error correction. But fault tolerance, like how many faults do we need to tolerate? Well, it depends on the application. If we're looking at just distance 3 fault tolerance, we're just looking to tolerate one fault. But for distance 5 fault tolerance, we're looking to tolerate 2 faults. So let's look at some of the rules for fault tolerance. If there's one fault that occurs during my circuit, then I need to ensure that the weight of my output error is at most 1. It can't be 2. In the case of 2 faults, however, we don't really care what the weight of the output error is for the distance 3 case. But for the distance 5 case, where we do care what the weight of the output error is, we need to ensure that 2 faults causes at most a weight 2 data error. So now that we have some of the basics down, I think we can talk about the results quickly. The main question we ask here is, how many extra qubits do you need to perform distance 3 fault-tolerant measurement of a weight W stabilizer? And this was initially shown by Shor to be equal to W plus 1. Through a few improvements, this was brought down to W by 2. The first one was an ancilla cat decoding trick, which was used by DiVincenzo and Alaferis, and they brought it down from W plus 1 to W. And then a 2 times compression trick, which was actually found independently in like a couple of papers from 2014 to 2017, which brought this number down from W to W by 2. And using our new techniques of traversing paths through the hypercube, we can show that you can get a logarithmic overhead. So distance-free stabilizer measurement, in fact, just requires log W plus 1 extra qubits. And as a bonus, we get distance-free cat state preparation. So let's go through each of these different protocols and see what tricks were used to move from the Shor scheme to our results. Let's start with the Shor scheme. The idea behind the circuit is really simple. You prepare a 5-qubit ancilla cat state if you want to measure a weight 5 stabilizer. But the first thing you do is you non-fault tolerantly prepare this 5-qubit cat state. And then you perform parity checks using 1 extra qubit. By performing these parity checks, you can ensure that you've prepared your cat state fault tolerantly. And if you've prepared your cat state fault tolerantly, then the weight of an output error of the cat state is at most 1 for 1 fault occurring during the cat state. So after you prepare your cat state fault tolerantly, you attach 1 data C0 to each of the ancilla wires. You do this because if you attach multiple data CNOs to a single ancilla wire, 1 fault in the circuit might spread to a high weight data error. And that's something we want to stop from happening. So this circuit is well and good. You use a W qubit ancilla cat state to measure a W qubit stabilizer, and you use 1 extra qubit for a parity check. Now let's look at the cat state decoding trick. So in this circuit, there's just one minor difference. The difference is that you non-fault tolerantly prepare the cat state, and you don't apply parity checks using extra qubit to ensure that the cat state is fault tolerantly prepared. Instead, you just directly measure the stabilizer on the 5 qubits, and now you unprepare your cat state. And in the process of unpreparing your cat state, you ensure that the syndrome information is left on only the bottommost qubit, which is measured in the X basis, and all of the other ancilla qubits, these 4 qubits measured in the Z basis, all of them can be used to diagnose X faults on the ancilla qubits that can spread to high weight data errors. So based on the measurement outcomes, you can perform corrections onto the data qubits. This reduces the overhead by 1, but the plus point is at least it lets us correct for high weight data errors. The next trick used was the 2 times compression trick. So to understand how this 2 times compression trick works, let's look at the effect of X faults at 2 locations in the ancilla circuit, at the brown and the blue X locations marked in the circuit. So the brown X fault will propagate down this data C0 into an X error. And the blue fault will not propagate down to the data at all because there's no data C0s after the blue fault happens. So although they form different errors on the data qubits, these 2 faults give us the same data, give us the same error on the ancilla qubits. And when you measure these qubits in the Z basis, the X error triggers the Z measurement, and you end up getting the 0010 flag measurement outcome, which corresponds to one particular correction. And let's look at what happens when you actually apply this correction when you observe this flag measurement outcome. So if you apply this X correction to the brown X fault, it gets transformed into the identity on the qubit, and the blue X error, the blue X fault would in fact be transformed into an X error on the same data qubit. But this is fine for distance-free fault tolerance because we just need to ensure that if 1 fault occurs in the circuit, that the weight of the output error is at most 1. So now let's see what happens if I introduce another data C0 using the same ancilla wire. So this will be a data C0 placed just before the brown X fault. and this gives rise to a new fault location. So let's look at the effect of an X fault at the green X location now. Now this green X fault spreads down to 2 data qubits into this XX data error. But when you apply the same correction, it turns out that the output error is one of these three, XI or II or IX. And in all three of these cases, we can satisfy the rules for distance-free fault tolerance because the weight of the output error is at most 1. So that's amazing. You can attach 2 data CNOTs to each ancilla wire instead of just 1 data CNOT. And that's how you get a weight 10 stabilizer measurement circuit from the weight 5 stabilizer measurement circuit. Let's actually take a closer look at the flag configurations now, the observed flag configurations. Each of these flag configurations corresponds to some string of 1s and 0s. Essentially, it's just some binary string. Since it can be represented as a binary string, well, now you can represent each of these flag configurations as vertices on a hypercube. In this slide, I've represented the hypercube using this diamond shape, where I've ordered the vertices of the hypercube in terms of Hamming weight, and I put the lowest Hamming weight vertices at the bottom with the highest Hamming weight vertices at the top. Now let's look at which vertices of the hypercube are used by the compressed deviant tensor Alpha-Ferris method. Notice here that they use all of the weight 1 vertices and 1 each of the higher weight vertices. And that's how you get this these red circles in this diagram. This horizontal row of vertices corresponds to the weight 1 vertices, and each one, this column of vertices corresponds to each of the higher weight vertices used. So this is actually where the inefficiency comes from. Notice here that a lot of the hypercube is left unused. And so we show that it's actually possible to almost use nearly all 2 to the A vertices of the hypercube. How do we do this? Well, the main difference between our technique and the compressed deviant tensor Alpha-Ferris technique is in the ancilla block. In this method, the catch state is non-fault tolerantly prepared completely before any of the data CNOTs are applied, and the catch state is completely unprepared completely after all of the data CNOTs have been applied. In our case, we prepare and unprepare the ancilla catch state while measuring the stabilizer. So let's take a look at what actually happens in our circuit. Notice that we again use the 2 times compression trick. So X faults at any one of these 3 green star locations will obviously give us different data errors, but we know that they give us the same flag configuration, and associated with the flag configuration is a correction. As long as the correction works for all 3 of those faults, it's valid. So let's take a closer look at what the observed flag outcome is for each of these 3 faults. An X fault at any of these 3 locations propagates an X error into the red wire through this red ancilla CNOT, and that triggers a flag configuration of 001, which is also exactly equivalent to this pattern of hollow and filled squares I have just above the possible faults. What if I have faults occurring just before this yellow CNOT though? Well, in that case, the X error would propagate up into the yellow wire and into the red wire, giving me a flag configuration of 011. So notice here that by applying this yellow CNOT, I've essentially transitioned from the 011 vertex of the hypercube to the 001 vertex of the hypercube. I've moved along an edge of the hypercube. By arranging each of these flag configurations in the form of a sequence, notice that you end up tracing out a path through the hypercube. And the length of this path, we show that it's 2 to the A minus 2A plus 3. The reason for this is because we access none of the weight 0, so we don't use the weight 0 configuration. We use only 2 of the weight 1 configurations, only at the end and at the start. And all of the vertices used in between are of higher weight. But it turns out that we also don't use some of the weight 2 vertices in our path. So let's compare the compressed DiVincenzo-Alfieri method to our method. In the compressed DiVincenzo-Alfieri method, only 2a minus 1 vertices are used, which is linear in the number of flag ancillas. But in our method, we use 2 to the a minus 2a plus 3 vertices, which is exponential in the number of flag qubits used. So that's where we get the exponential improvement in qubit overhead. So in the paper, we also show that this path is actually of optimal length. You can't get a path that's longer than 2 to the a minus 2a plus 3 vertices. The only thing left now is to find out how to construct this path on the hypercube. And to do that, we use an inductive construction technique where we look at the path on the a minus 1 dimensional hypercube and try to construct the path on the a-dimensional hypercube. So it just follows 4 simple steps. You copy the first n-1 vertices of the previous path down and append a 0 at the bottom for the new flag qubit. Then you mirror this block and you append a 1 at the bottom. And to the new block that you've just appended, you then swap the rows 2 and a minus 1. And you finally apply a cleanup operation at the end where you add in some extra vertices you pad in some extra vertices at the end. So by doing so, you get this path of length 2 to the a minus 2a plus 3. Notice here that in the 3-dimensional hypercube, you have a path of length 5. And in the 4-dimensional hypercube, you have a path of length 11. So using this length 11 path, you can actually measure the stabilizer. You can actually measure a weight 22 stabilizer. And so this is the main result of our talk. It's that using m ancilla qubits, where one ancilla qubit is used for your syndrome ancilla, and the other ancilla qubits are used as flag ancillas, you can essentially measure a W qubit stabilizer, fault-tolerant to distance 3 for W less than 2 times 2 to the m minus 1 minus 2m minus 1 plus 3. And this factor on the right comes from the length of the flag hypercube path. The factor on the left comes from the 2 times compression check. So if you rewrite this equation, then you end up seeing that the number of ancillas you need actually grows only logarithmically in the weight of the stabilizer being measured. So until now, we've spoken about slow reset, where none of the ancilla qubits can be reset while measuring the stabilizer. You need to maintain the state of the ancilla qubits until the stabilizer has been completely measured. But in the case of fast reset, the ancilla qubits can be reset in the middle of measuring the stabilizer. And so if we're given this flexibility, we show that you only need 1 syndrome ancilla and 3 extra flag ancillas. How do you use these 3 extra flag ancillas? Well, starting with this red qubit here, you start off with a weight 1 flag configuration, and by using a yellow qubit wire and a third purple qubit, you end up with a weight 2 flag configuration and a weight 3 flag configuration. But then you don't have any more qubits to add to this to give you higher weight flag configurations. So what do? You measure the first red ancilla, and then you reinitialize it. And by doing so, you transition between, you switch off the top bit, so it's now 0. And now you're left with a weight 2 flag configuration, which is not the same as the first weight 2 flag configuration. Notice, because the first weight 2 flag configuration was on the first red and the first yellow ancilla wire. Here, however, it's on the first yellow and the first purple ancilla wire. So after you reinitialize your red ancilla, you can again transition into a weight 3 flag configuration. Then you switch off the yellow ancilla, reinitialize that, and again you switch between a weight 2 and a weight 3 flag configuration. So essentially, you just keep switching between weight 2 and weight 3 flag configurations by switching off the oldest flag ancilla and reinitializing it so you can use it fresh. Our results can also be used for cat state preparation. So if you look at this circuit, this is a weight 6 stabilizer measurement circuit, fault tolerant to distance 3, with three observed flag configurations, essentially the two-dimensional hypercube, or the two-dimensional square. So the correspondence between the stabilizer measurement circuit and the catch-state preparation circuit is that the bottommost data qubit is removed. So you have a total of 6 data qubits. So the cat plus qubit plus 5 extra ones. And in the catch-state preparation circuit, you have to initialize the data qubits in the cat 0 state. Whereas for the stabilizer measurement circuit, you're operating on a set of qubits that are already in a quantum error correcting code. So using another improvement, we show that if you prepare your cat state non-fault tolerantly and then use the flag sequences for parity checks after you've non-fault tolerantly prepared the cat state, then you just need one ancilla. The reason for this is that the yellow C naughts and the red C naughts in the circuit all commute. And because of that, you can use this one ancilla to first apply all of your yellow C naught gates, and then you measure, reinitialize, and then apply all the red C naught gates, and then you measure again. And based on the measurement outcomes, you then perform corrections. So we show that if you use this technique, the number of ancilla qubits you need grows only as log of W by 3 plus 1, not log of W plus 1. So this protocol is actually a little bit more efficient than the protocol to measure a weight W stabilizer. And with that, I'd like to conclude. So what have we seen in this talk? We've seen that measured flag configurations in fault-tolerant stabilizer measurement circuits can correspond to vertices on the hypercube. And by traversing through the paths on these hypercubes, you can exploit maximal length paths for more efficient fault tolerance. By efficient here, I mean using a few ancilla qubits to measure a high weight stabilizer. The results we've accumulated are as follows. Distance 3 stabilizer measurement now needs at most log W plus 1 extra qubits, as opposed to the W by 2 linear overhead of the previous existing protocols. And we also introduced the study of asymptotic resource requirements of distance 3 cat state preparation, which needs at most log W by 3 plus 1 extra qubits. So now on to future work. So thus far, all the circuits in this talk have been about distance 3 fault tolerance. But the natural next question is, can we get higher distance fault tolerance? And in this circuit, I show how to measure an arbitrary weight W stabilizer fault tolerantly to distance 5. But here we use W by 2 qubits, and it's not logarithmic. So the question is, can it be brought down to logarithmic in the weight of the stabilizer W? The next thing we looked at is geometry and locality constraints. Here we show a weight 4 stabilizer measurement circuit, which is fault tolerant to distance 3. And we show that these 7 qubits can actually be arranged in the form of this 2D grid with only nearest neighbor interactions. So this is interesting for superconducting type quantum computers because they have circuits that need to be fit on a 2D grid. But in the case of, say, ion trap quantum computers, which have all-to-all connectivity, you can just directly use the circuits from a paper. Another question we looked at is parallel cat state preparation using one block of flag ancillas. And in this circuit, we show how to prepare a 2 weight 4 cat states fault tolerantly to distance 3. And by distance 3, I mean that the ancilla block is fault tolerant to distance 3, meaning it tolerates one fault. So an open question here is, can you make 3 weight 4 cat states fault tolerantly to distance 3? Can you make n cat states fault tolerantly in parallel using one block of flag ancillas? And the answer is yes, but there aren't any actual upper bounds on any of these questions just yet. So that's a big open question. We also looked at the flag-based state preparation of general CSS codes. So we showed that flag-based techniques can be used to prepare cat states fault-tolerantly. Cat states are basically just stabilizer states of some CSS code. So we asked if it is possible to use these flag techniques on more complex CSS codes. And so in this circuit, I show how to prepare the encoded cat0 state of the Steam code, the 713 Steam code, using just 3 extra flag ancillars. So an open question is to see how far we can take this. Like, if we get distance 7 fault-tolerant circuits, can we use them to create, say, logical cat0 state prep of the Golay, the 2317 Golay code? So yeah, there are a couple of open questions here. And with that, I'd like to thank everyone for attending my talk.